Section 6.1, Newtonian Gravitation. In this section, we're going to take a look at Newton's law of universal gravitation. This law states that there's a gravitational attraction between any two objects. If the objects have masses m1 and m2, and their centers are separated by a distance r, the magnitude of the gravitational force on either object is directly proportional to the product of m1 and m2 and inversely proportional to the square of r. Newton's law of universal gravitation can be summarized with this equation. F capital G is equal to G m1 m2 over r squared, where m is mass 1, m1 is mass 1, m2 is mass 2, and r is the distance in between them. Capital G is the gravitational constant. This value is 6.67 times 10 to the power of negative 11 newtons times meters squared per kilogram squared. You will be able to find both the equation and this constant on your formula sheet. Let's start with sample problem number 1. Calculating the force of attraction between two ordinary masses. The centers of two uniformly dense spheres are separated by 50 centimeters. Each sphere has a mass of 2 kilograms. So let's start by writing down what we know. We know mass 1 is 2 kilograms. Mass 2 is also 2 kilograms. And the distance between these two is 50 centimeters, or 0.500 meters. And our job is to find the gravitational force of attraction, F capital G. Using the equation from above, the gravitational force of attraction is equal to G m1 m2 over r squared. Now we can sub in our values. We know that G is 6.67 times 10 to the power of negative 11 newtons times meters squared per kilogram squared. M1 is 2 kilograms. M2 is 2 kilograms. All over 0.500 meters. And don't forget to square it. If we punch this into our calculator, we end up with a very small force, 1.07 times 10 to the power of negative 9 newtons. Therefore, the magnitude of the gravitational force of attraction between the two spheres is 1.07 times 10 to the power of negative 9 newtons. How much of an effect will this force have on the two spheres? Well, the gravitational force of attraction between the two spheres, which is 1.07 times 10 to the power of negative 9, is too small to have any noticeable effects on the motion of these two spheres under any normal circumstances. If these two objects were still in space, eventually over time, this small force would cause these two objects to accelerate towards each other. But under normal circumstances, the force is way too small to have an effect. Let's try sample problem number 2. Eris, a dwarf planet, is the 9th most massive body orbiting the Sun. It's more massive than Pluto and 3 times farther away from the Sun. Eris is estimated to have a radius of approximately 1,200 kilometers. Acceleration due to gravity on Eris differs from the value of G on Earth. In this 3-part problem, you will explore the force of gravity on the surface of Eris. Part A. Suppose that an astronaut stands on Eris and drops a rock from a height of 0.30 meters. The rock takes 0.87 seconds to reach the surface. Calculate the value of G on Eris. So we know that it is the force of gravity on Eris that is causing this object, this rock, to accelerate from this height of 0.30 meters to the ground. So we're given the vertical displacement. We know the time it takes to fall, that's 0.87 seconds. And what we need to find is the acceleration in the y direction, which is equivalent to the gravitational field intensity of this planet. We're going to look to our kinematics equations. Since this object was dropped from rest at a height of 0.30 meters, the initial velocity, v1y, is 0. Therefore, we can cancel out this term right here. This allows us to solve for acceleration in the y direction by rearranging for acceleration. We see that acceleration is equal to 2 delta dy over delta t squared. We can sub and solve. It's 2 times 0.30 meters. I'm going to use a negative sign to imply that this was going in the down direction, divided by delta t, which is 0.87 seconds. Punch this into our calculator and we get negative 0.793 meters per second squared. So we can say that the gravitational field intensity on Eris is equal to 0.793 newtons per kilogram. Remember that newtons per kilogram and meters per second squared are equivalent, and the direction is down. So to two significant digits, the value of G on Eris is 0.79 meters per second. Now we want to calculate the mass of Eris. So force of gravity, we have two equations for it. We have Fg, which is equivalent to m times the gravitational intensity on Eris. Or you can use Newton's law of universal gravitation, F big G, where it's equal to G, the mass of an object, times the mass of Eris, divided by the radius of Eris squared. So if we're looking at, for example, the mass of any particular object, we can use either one of these equations to find the force of gravity. They are equivalent to one another. Now, we don't know what object we're talking about or the mass of this object, but we do know that if we set these equal to each other, we can actually cancel these guys out. So what we're left with is the gravitational field intensity of Eris is equal to the gravitational constant times the mass of Eris divided by the radius of Eris squared. Our job is to find the mass of Eris, and we can do this by rearranging. It's equal to the gravitational field intensity of Eris, which we found up above, times the radius of Eris squared divided by the gravitational constant. Let's sub these values in. We have 0.79 newtons per kilogram times a radius of 1,200 kilometers, which is 1,200 times 10 to the power of 3 meters. We're going to square this value, and we're going to divide it by 6.67 times 10 to the power of negative 11 newtons times meter squared per kilogram squared. If you punch this into your calculator, the mass of Eris is equal to 1.7 times 10 to the power of 22 kilograms. In part C, suppose that an astronaut stands on Eris and drops a rock from a height of 2.50 meters. Calculate how long it would take the rock to reach the surface. So we know the vertical displacement is negative 2.50 meters. Put the negative sign to imply that it is falling down. We know the acceleration in the y direction on the planet Eris is negative 0.79 meters per second squared, because the acceleration in the y direction is equivalent to the gravitational field intensity on the planet. And our job is to find delta t. Delta D is equal to V1 delta T plus 1/2 A delta T squared. Again, since V1 is 0, this term cancels out, and we rearrange for delta T. This is something we've done many times, especially in Unit 1. Delta T is equal to the square root of 2 delta dy over AY. We can sub this in. That's 2 times negative 2.50 meters divided by negative 0.79 meters per second squared. Hopefully what we have underneath our square root is a positive number, because we can't take the square root of a negative number. If you punch this into your calculator, you should end up with 2.5 seconds. Therefore, it would take the rock 2.5 seconds to fall 2.50 meters. Okay. Sample problem number 3 is going to look at the force of gravity on a 3-body system. So we have object A, object B, and object C. The diagram below shows 3 large spherical asteroids in space, which are arranged at the corners of a right-angled triangle ABC. Asteroid A has a mass of 1 times 10 to the power of 20 kilograms. Asteroid B has a mass of 2 times 10 to the power of 20 kilograms and is 50 million kilometers, 5 times 10 to the power of 10 meters from asteroid A. Asteroid C has a mass of 4 times 10 to the power of 20 kilograms and is 25 million kilometers, 2.5 times 10 to the power of 10 meters away from asteroid A along the other side of the triangle. Determine the net force on asteroid A from asteroids B and asteroid C. So what we're going to look at is the force on asteroid A from B, and we're going to use Newton's law of universal gravitation to find that out. Then we're going to find the force of asteroid C on asteroid A using Newton's law of universal gravitation. And then we're going to use Pythagorean theorem to find the net force of these, since they form a right-angled triangle. So let's start subbing in these values. 6.67 times 10 to the power of negative 11. To conserve space on this paper, I'm going to omit the units. The mass of asteroid A is 1 times 10 to the power of 20 kilograms. The mass of asteroid B is 2 times 10 to the power of 20. And the radius, or the distance between these two, is 5 times 10 to the power of 10 meters squared. If you punch this into your calculator, you should get 5.3 times 10 to the power of 8 newtons. Let's do the same for the force that asteroid C provides on asteroid A. Now, these values should be the same. I'll write them out since you have to write them out as well. I won't be lazy. 10 to the power of negative 11, 1 times 10 to the power of 20. Now this much more massive asteroid is 4 times 10 to the power of 20 kilograms. And the distance between them, it's a bit closer. It's 2.5 times 10 to the power of 10. Make sure we square it. Punch this into your calculator and you should get a larger force. We get 4.3 times 10 to the power of 9 newtons. Okay, so the force of asteroid B on A is in this direction. The force of asteroid C on A is in this direction. If we add them, because they're vectors, tail to tip, we can find the net force like so, where the net force, Pythagorean theorem, is equal to the square root of FAB squared plus FAC squared. It's equal to the square root of 5.3 times 10 to the power of 8 squared plus 4.3 times 10 to the power of 9 squared. If we punch this into our calculator, the net force acting on asteroid A from both of these asteroids is 4.3 times 10 to the power of 9 newtons. And we have to find out what direction. And we're going to use this angle theta. Theta will be equal to the inverse tan. The opposite is 4.3 times 10 to the power of 9. And the adjacent is 5.3 times 10 to the power of 8. Punch this into our calculator. And theta is 82 degrees. And that is 4.3 times 10 to the power of 9 newtons, 82 degrees east of north. Perfect. The textbook writes this as 4.3 times 10 to the power of 9 newtons, 7.1 degrees north of east. Know that, actually this should be, I apologize, rounded to 83 degrees. Note that (7.1 degrees north of east and 83 degrees east of north are equivalent. Awesome. Now let's determine the net force on asteroid B from asteroid C. First thing we're going to do is find the distance between asteroid B and asteroid C. We're going to find this distance here. Asteroid BC distance. We're going to use the right angle triangle again in Pythagorean theorem. It's going to be equal to RAB squared plus RAC squared, square root. That's the square root of 5 times 10 to the power of 10 squared plus 2.5 times 10 to the power of 10 squared. Punch it into our calculator, and we get 5.6 times 10 to the power of 10 meters. That's the distance between these two. Good. Now we're going to use Newton's law of universal gravitation to find the force of attraction between asteroids B and C using G MC over RBC squared. That is 6.67 newtons times meters squared per kilogram squared times. I probably should have omitted these units to save space. Be mindful of your space. The mass of asteroid B is 2 times 10 to the power of 20 kilograms. The mass of asteroid C is 4 times 10 to the power of 20 kilograms. And we just determined the radius, or the distance between them, which is 5.6 times 10 to the power of 10 meters squared. So the force of asteroids C and B, if we punch it into our calculator, is 1.7 times 10 to the power of 9 newtons. Now let's determine the angle. And to determine the angle, we're going to find this angle right here, theta, in the right angle triangle, where RAC is our opposite to that angle and RAB is our adjacent. So theta is equal to the inverse tan of RAC over RAB, which is the inverse tan of 2.5 times 10 to the power of 10 over 5.0 times 10 to the power of 10. If you punch this in, you get 27 degrees. And that's 27 degrees east of south. Therefore, the force between asteroids B and C is 1.7 times 10 to the power of 9 newtons, 27 degrees east of south. Very good. Now let's look at the concept of gravitational fields. The universal law of gravitation tells us that at any point in space surrounding a massive object, such as the Earth, we can calculate the gravitational force on a second object sitting at this point in space. A vector exists at every point in space surrounding the central object, pointing towards it and depending on the object's mass and the distance from its center. The gravitational field of the central object can be represented by this collection of vectors. A gravitational field exerts forces on objects with mass. The gravitational field strength is the force of attraction per unit mass of an object placed in a gravitational field and equals the gravitational force on the object divided by the object's mass. On the surface of Earth, the gravitational field strength is approximately 9.8 newtons per kilogram. Definition of a gravitational field is a collection of vectors, one at each point in space, that determines the magnitude and direction of the gravitational force. The closer you are to the surface, I want to highlight this, the larger these force vectors are. The farther you are from the surface, the smaller the field intensity or the field lines are. These field lines will show the magnitude and the direction of the force, all of them pointing towards the center of the very large object, Earth. The closer you are to the surface, the larger the force. Now, the gravitational field strength, the definition is the magnitude of the gravitational field vector in a point in space. As you get closer to the surface of the Earth, these values will approach 9.8 newtons per kilogram. As you move farther from the center of the Earth, these values, the value for the field intensity of the gravity on Earth is smaller. In general, we can calculate the gravitational field strength on a planet by using a simplification of Newton's law of universal gravitation, where we have the gravitational field intensity is equal to the gravitational constant times the mass of the planet and the radius of the planet. If you put in the mass of the Earth and the radius of the Earth, you will get the value G for the gravitational field intensity on Earth, 9.8 newtons per kilogram. If you did the same, but instead used the mass of our moon and the radius of our moon, you'd get a different value. You would get the gravitational field intensity of our moon, which is about 1/10 the gravitational field intensity on Earth. It's 1.6 newtons per kilogram down. Let's try some sample problems that deal with gravitational field strength. Determining the gravitational field strength. Calculate the magnitude of the gravitational field strength on the surface of Saturn, assuming that it's perfectly spherical, with a radius of 6.03 times 10 to the power of 7 meters, and the mass of Saturn is 5.69 times 10 to the power of 26 kilograms. So the gravitational field intensity on Saturn is equal to Gm Saturn divided by the radius of Saturn squared. Sub in our values, 6.67 times 10 to the power of negative 11 newtons times meters squared per kilogram squared, times the mass of Saturn is 5.69 times 10 to the power of 26 kilograms, and divide this by the radius of Saturn, which is 6.03 times 10 to the power of 7 meters. Don't forget to square it. Punch this all into our calculator, and you end up with 10.4 newtons per kilogram. Therefore, the gravitational field strength on the surface of Saturn is 10.4 newtons per kilogram. Let's determine the ratio of Saturn's gravitational field to the Earth's gravitational field. So, the gravitational field of Saturn divided by the gravitational field of the Earth. Don't like the way that G looked. I'm going to make a regular G. Is 10.4 newtons per kilogram, and on Earth it's 9.8 newtons per kilogram. Divide these two, you end up with 1.1. So we can say that the ratio of Saturn's gravitational field strength to Earth's gravitational field strength is 1.1 to 1. Okay, great. For homework, try practice problems on page 293, 295, as well as review questions on page 296, numbers 1 to 13.